Good morning, everyone. My name is Junjie. Thanks to the Flex conference for providing this opportunity to present our research. Today, my presentation topic is flexible direct write printed radio frequency sensor for RF sensor. Why do we need ice detection? With global warming, our world will suffer great impact on intensity and the frequency of extreme weather. Extremely low temperature and severe icing can cause material fatigue, poor performance, which in turn lead to destruction of infrastructure. For example, in an ice event, the weight of ice will put additional pressure on the power transmission line and increase the possibility of power failure due to the ice accumulation. In early of this year, an ice storm triggered a power crisis in US Texas. The damage from the blackout are estimated at least $195 billion. If we can quickly and effectively know whether some important infrastructure are freezing, we can take action to protect these infrastructures from damage. Currently, there are several ice detection systems used different techniques in market, like ultrasonic measurement, resonance measurement, infrared measurement, and capacitance measurement. However, due to the sensor mechanism, these ice detection systems have certain limitation in some practical application. Practically, in terms of reduced read range for the wireless measurement, or due to require complex active sample circuit. So there is a need for a reliable and low-cost ice detection sensor to help reduce the ice-related risk of urban infrastructure under extreme weather conditions. Printed radio frequency sensor has been extensively researched in various applications, gas detection, healthcare monitor, and food processing, because it can not only perform the wireless sensing, but also quickly protecting and reduce manufacture cost. In this research, a dispenser print RF loop antenna is proposed for ice detection application. The rectangular antenna is designed with a length of 14 millimeters, a width of 24 millimeters, and a line with 2 millimeters. The antenna was designed to resonate at 2.4 GHz for the proposal sensor to be able to operate wireless in the industrial, scientific, and medical band. As shown in the right figure, the design antenna was printed on flexible polyimide substrate using a commercial dispenser printer. A flexible silver ink used as the conducting material for the antenna. After the printing process is complete, the polyimide film, which is carrier substrate, is cured on a hot plate. Once the antenna is cured, the polyimide film is removed from its substrate, and SMA connector is soldered to connect with the antenna. To demonstrate the effectiveness of the printed loop antenna in ice sensoring, the fabricated RF antenna sensor was covered by an ice ring, as shown in right figure. The measurement was carried on by connecting the antenna to a VNA measurement device. Also, to investigate the feasibility of the wireless ice detection. 2.1 dB halfway dipole is utilized as receiver. The measurement setting is shown in the right and the middle figure. In the next slide, the left figure shows a simulation S11 reflection coefficient of the proposal loop antenna. It clearly demonstrates the relation between the thickness of the ice and the S11 response of the antenna. In this figure, for 1 millimeter thick of ice, the antenna can clearly detect the ice built up with over 200 megahertz resonant shift and more than 20 dB change in the S11 magnitude at 2.4 gigahertz. For 10 millimeter thickness ice, a frequency shift of 680 megahertz is observed. The right figure shows the simulate and the measurement S11 of the printed loop antenna with and without a layer of ice. The very close agreement between the simulate and the measurement result for the unload antenna indicate the high accuracy and the good performance of the proposal antenna. For 9 millimeter thick ice result, it can be observed that the simulate and the measurement reflection coefficient indicate a frequency shift about 700 megahertz from 2.4 gigahertz. However, there's a slightly different between the simulation and the measurement result. When it's uncovered by the ice. In contrast, the simulation matched the measurement result also perfect with the ice. The reason for this difference may be the gap between the antenna and the ice ring. Due to the shape of the ice ring can't completely cover the antenna. In next slide, this figure demonstrates a clear trend between the thickness of the ice and the S21 response of the loop ice sensor. From this figure, it can be observed that the gain sensitivity of the antenna is around 9 dB for 9 millimeter thickness of the ice at 2.4 gigahertz. License-free band. In a real-world application, this demonstrated that the RF sensor can be connected to Bluetooth or Wi-Fi transceivers, where the sensor response could be detected through the signal strings at the receiver. In summary, RF antenna-based sensor for ice detection was proposed based on a flexible print loop antenna. The RF loop sensor is designed for operate 2.4 gigahertz. In its S11 profile, it can be detected that as the ice thickness on the antenna surface increased to 9 millimeter, the resonant frequency decreased from 2.46 gigahertz to 1.78 gigahertz, and with a magnitude change from minus 32 dB to minus 18 dB. In addition, the printed RF sensor can be well measured with a sensitivity of 9 dB for 9 millimeter thickness ice. This technical offer an expensive, flexible method to wireless detect eyes in future urban infrastructure application. The next step of our research is improve the antenna design for increase the resolution of thicker eyes sensory or eyes accumulation rate. The second target is connect the sensor. The sensor is connected to a Bluetooth or Wi-Fi device, like mobile phone, to form a eyes detection system. This is my presentation. Thank you for listening.